So that's the AD9375 device. So what are we wrapping around this to make it easier to use and enable evaluation, development, and prototyping? So last year we launched RadioVerse, which is our technology and design ecosystem that helps solve our customers to solve complex radio challenges. At the core of RadioVerse, we've got our market-leading ADI radio technologies, devices such as the AD9371, AD9375. In order to make those more accessible and to accelerate our customers' time to market, we introduced an ecosystem of tools, documentation, reference designs, and modules that enables faster evaluation, prototyping, and gets into production faster. Wrapped around that again, we've got a stable of best-of-breed partners, and these partners bring specific elements of expertise or IP to the table that analog devices may not have and our customers may not have, but everyone recognizes is required in an end application. And so they bring that piece of the puzzle that might be missing in a particular engagement. And then wrapped around that again, we've got the market-specific insights, ideas for roadmap planning that provide some context around what's happening in the market, what's happening with the technology that helps guide decisions. So what specifically do we have for the AD9375 then on RadioVerse? So there's a number of elements to it. We've got evaluation kits, the AD9375-N/PCBZ is the daughter card that you see on the right there. That comes with a Skyworks PA evaluation card. And what this enables is straight out of the box, you can hook up a known good high efficiency PA with our DPD and get that linearization running straight out of the box before proceeding to either using that PA in a product or testing with a different PA. In terms of carrier platforms, the board interfaces to the Xilinx ZC706 FPGA motherboard. We've got simulation tools, so we've worked with MathWorks on MATLAB filter wizards and a Simulink model. I've talked a bit about the API that we provide in terms of a software driver, and then in terms of evaluation, we have our standard GUI to operate the functions of the AD9375, the standard transmit, receive, frequency functions, etc. And then we've also added a DPD GUI that allows tuning of the DPD algorithm if necessary. In terms of customer support, support comes via our ADI engineer zone, where we've got a variety of forums depending on whether the question is related to the RF transceiver, the analog components, the API, the drivers, or indeed the FPGA reference design. And then finally, we've got some reference designs and partnered with some companies on more complete solutions. So I'll talk a little more about a small cell radio reference design that we did in conjunction with Benetel, who are a radio solutions provider, and also some tested PA reports that we've done in collaboration with PA vendors. So digging into more detail then on the tested PA reports. So we've worked with leading PA vendors to test our DPD with their PAs, optimize the performance, and show reports up on our website, which enable you to get to market faster with a ready-to-go solution. So there's a selection of PAs that have been tested and optimized for performance with the AD9375 DPD, complete reports that detail the linearization performance before and after DPD, efficiency across frequency and output power, all contained in these reports. And then, crucially, the PA and DPD settings have been captured so that these results are easy to replicate. And so, going a step further then, we're also introducing alongside the AD9375 our small cell radio reference design with integrated DPD. So as I mentioned, we worked with our RadioVerse Alliance partner Benetel on this solution. It's a complete JSD204B to antenna design, as you can see in the diagram. So the functionality it implements is 2x2 LTE 20 megahertz with 250 milliwatts output power per antenna, and it's BOM reconfigurable to other bands. It contains all the solutions. So as you can see in the diagram on the right, you've got the AD9375 transceiver, you've got the ADL5355 VGA, a power amplifier, circulator, and duplex filter, and then on the receive side you've got LNAs, filters, all the way back into the device and out through the JSD204B interface. So all those components are on board, and in addition there's the ADP5054 power solution. This is implemented in a very small form factor, so 88 millimeters by 83 millimeters. So the key benefits here are enabling you to get to market faster with a proven reference design for small cell radios. Enhanced R&D efficiency with a common platform design that's easily reconfigured to other bands. So we specifically chose the PAs, LNAs, and filter components such that they have pin-compatible alternatives for different frequency bands. So that enables easy rebanding of this design. And this is the lowest power, smallest form factor, 250 milliwatt small cell radio that's available on the market due to the combination of the AD9375 and some high efficiency PAs. And just a little more detail, so it operates off a single 5-volt supply. The total power consumption is just under 10 watts. Typical ACLR, or adjacent channel leakage ratio, is minus 54 dBc at the 24 dBmp out, or 250 milliwatts. As I mentioned, it's a broadband design. The one we've released is an LTE band 7 FDD design, and it is BOM reconfigurable to other 3GPP bands. The PA on board is a high efficiency Skyworks 66279 PA. And this interfaces to the same Xilinx motherboards, ZC706, as our standard eval card via an interposer that comes along with the reference design. Okay, so just to summarize then, so the transition from 4G to 5G technology is underway, and you'll be seeing that coming over the next number of years. Small cells and massive MIMO are key building block technologies that enabled enhanced capacity and coverage for operators, and these are two additional tools in the network operator's kit now as they go out and solve these capacity and coverage problems. Small cells and massive MIMO solutions then are a great solution for the operator, but they introduce challenges for the radio designer. The challenges are to reduce the radio size, weight, and power to enable the increased radio density required. The proliferation of band variance and output powers is a problem in terms of the matrix of combinations that must be brought to market. And then there's the time to market pressure in terms of the industry becoming more competitive. And we've launched the AD9375 targeting small cell and massive MIMO markets. And this solves the challenges of small cell and massive MIMO by providing the first wideband RF transceiver with integrated digital pre-distortion. It enables that disruptive system partition that reduces the radio size, weight, and power. The wide RF tuning range enables a common platform that counters the proliferation of band variance and output powers that's happened. And then in terms of resolving the time to market pressure, we provide a complete ecosystem of PA reports, eval tools, and the small cell radio reference design, and all of these help accelerate time to market. So that's it. Thanks for listening. I'll hand you back over to Murray.
All right. Thank you, Peter. Let's now jump right into the Q&A. First question, a listener wants to know, what limits the bandwidth to 40 megahertz?
Okay, thanks. So yeah, that's a good question. So the DPD algorithm itself has two memory taps, and as the bandwidth of signals going through PAs increases, the memory component of the distortion in the PA increases. And so there's a limited capability in the digital pre-distortion to correct for that. And so typically, it's quite PA dependent, but typically we see 40 megahertz as being the level that the DPD is comfortable at operating at. And so, you know, the DPD was designed specifically for these kind of small cell and massive MIMO applications, and that's the trade-off that we took when designing the DPD, was to limit the functionality and the memory of the DPD so that it could be made very small, very low power, and make it integratable.
Mm-hmm. Our next question is from a listener who asks, what kind of efficiency is achievable with PAs used with this DPD?
Okay, so I guess in terms of the LDMOS PAs that I showed earlier in the slide deck, those are typically operating in a 40 to 42 or 43% efficiency as you operate with this DPD, so that's for LDMOS. Then in terms of the high efficiency gas PAs that are available on the market, those are typically operating in the 30 to 35% efficiency kind of range. So those are the kind of ranges you can expect depending on the technology, and just by comparison then with a linear Class AB type amp, those will typically operate somewhere in the 10 to 16 or 17% sort of efficiency ranges.
Mm-hmm. Our next question is, this is pin compatible with AD9375. What about software compatibility?
Okay, so basically they are also software compatible. All that's needed is a few extra API functions to program the DPD specific functionality in the AD9375. So any work done in creating software drivers to drive the API on the AD9371 can be leveraged for the AD9375. All that's required is those few additional APIs to control that DPD functionality.
Okay, thank you. Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Analog Devices and Arrow for sponsoring today's event, and of course, all of you for joining. Have a great day.